Okay, section 3.3, we're going to be looking more at polynomials and more specifically how to find their zeros. So this is section 3.3. It's called zeros of polynomial functions. And we talked about polynomials, we've talked about functions. Remember what a polynomial is just a multi-term expression where all of the terms variable powers are whole numbers. We talked about binomial, trinomial, those are different types of polynomials. And then we talked about their degree. You could have a cubic, you could have a quartic, you can have a quadratic, or a linear polynomial. And then a function, remember a function was every x value just has one y value. At this point, we've spoken about x-intercepts. But now, every once in a while, you might hear the term root or zero, and they all mean the same thing. So what they mean is x values that make y equal to 0. All right. So if you do have a calculator, we're going to be using that storing technique that we talked about in a previous lesson. If you forget, I will go over that again. But so far, the way that we find the x-intercepts, roots, or zeros is we have a list. First thing we could do is just solve if it's simple. So for example, like if you had x plus 1 is 0, the x-intercept, root, or 0 would clearly be -1. But sometimes it's a little more complicated. We spent a lot of time talking about how to factor, and we have 4 different types of factoring. We have GCF factoring, we have grouping. Remember, grouping is with 4 terms. We also had trinomials, and we had special cases. Special cases, you should remember, generally people don't like these, but we have difference of squares, and the formula was a plus b times a minus b. And we also had cubics. You could add cubics, and the acronym that we used to figure out their signs was SOAP. Same, opposite, always positive. And if we, instead of adding cubics, if we were subtracting cubics, we would still use the same sign, opposite, and always positive. So after talking about factoring, we said some polynomials don't factor. If they don't factor, we could force them to factor by completing the square. And then if you don't like completing the square, I did show you where the quadratic formula came from in another post. But for anything you could complete the square on, you could also use quadratic formula. They are related. And then we're going to talk about a new technique today called the rational root or zero theorem. Now, when I talk about the rational root theorem, I usually use just RRT, just for short. So let's go over a few examples and we'll kind of build up to the rational root theorem. First example is determine if x minus 1 is a factor of 3x to the 5th minus 2x to the 4th plus x to the 3rd minus 8x squared plus 5x plus 1. And we've seen this in the last section. We have a few different ways to do this. We could use long division. We could use synthetic division. And we could use the remainder theorem. The remainder theorem would be the fastest way, but let's just make sure you remember your other techniques. So we'll do long division. x minus 1 divided into 3x to the fifth. Remember, if we're missing a term, we have to put 0 for that. And let's see, you could have 3x squared, so this would be 3x to the third minus 3x to the, what did I do here? Oh, that's to the fifth. So I need to multiply by x to the fourth. So then this, I misread my 5 over here as a 3. So then we get 3x to the fifth minus 3x to the fourth. If we subtract these terms, we get just x to the fourth, and then we'll bring down the x to the third. X times x to the third gives us x to the fourth, and if we multiply that out, we get x to the fourth minus x to the third. Again, we'll subtract those. So we get 2x to the third minus 8x squared. We're just bringing down these terms. X times 2x squared gives us 2x to the third minus 2x squared, which we have to subtract. And this would be negative 6x squared. Bring down the 5x. X times negative 6x gives us negative 6x squared plus 6x. Again, we'll subtract those. Get negative x plus 1. If we multiply by negative 1, we get negative x plus 1. Subtracting gives us a remainder of nothing. It's called long division. So determine if it's a factor. Well, it's a factor if the remainder is 0, right? And it is. So x minus 1 is a factor, which means, remember, x minus 1, if we make it equal to 0, x equals 1 would be a root, a 0, or an x-intercept. So you should be able to go back and forth between factors and x-intercepts and that kind of thing. Just set the factor equal to 0 and you can get the root, 0, or x-intercept. Okay, so now let's do synthetic division. This will be a little bit faster. Instead of using x minus 1, we'll use the root 1. And we have an x to the fifth, so I'll write the powers here to make sure I'm organized. And I'll write my coefficients. And let's go. Bring the 3 down. 3 times 1 is, we multiply going diagonally, we add going up and down. So this would be 3. So we get 1, 1, 2, 2, negative 6, negative 6, negative 1, negative 1, and a remainder of 0. I mean, we did that in, what, 30 seconds? So we get the same answer, and using the remainder theorem, what we're going to do is, if x minus 1 is the factor, x equals 1 would be the root, so we're going to figure out if this whole thing is f of x. Let's figure out f of 1. That would be 3 times 1 to the fifth minus 2 times 1 to the fourth plus 1 to the third minus 8 times 1 squared plus 5 times 1 plus 1. If you type that into your calculator, you get 0, which is the remainder. So all three of these techniques point us to the same answer. Is it a factor? Yes, it is. Okay, so let's do the next problem. Next problem says to factor 6x to the third plus 19x squared plus 2x minus 3 given negative 3 is a 0. Well, how many factors, or even better, how many roots are we supposed to get? The answer is 3, right? Because of what's called the fundamental theorem of algebra. And we did talk about this before, but what the fundamental theorem of algebra says is you'll get as many roots as the highest power of x. So we're supposed to get 3. Now what if I asked you to factor 8? You would say 8 is 2 times 4, or 8 is 2 times 2 times 2, right? Factor means write as a product. So we know that 6x to the third plus 19x squared plus 2x minus 3 is equal to, well, we know one of the zeros is negative 3, which means x is equal to negative 3. But if we're going to write, if the directions were to factor, right? So let's convert that root to a factor by bringing the 3 on the other side. So x plus 3 times something equals 6x to the third plus 19x squared plus 2x minus 3. Well, what if I told you 8 is equal to 2 times something? What would you do to find the missing piece? You would divide by 2, right? So for this problem, if you want to find the other factors, what we're going to do is divide 6x to the third plus 19x squared plus 2x minus 3 by x plus 3. And then this is going to be the quotient. So we could do long division. Synthetic division is a little faster. So let's use synthetic division. Negative 3 divided into 6x to the third, x squared, x, and then our number. And you can see that we do get a remainder of nothing. That's good. It's a factor, and we were told it was a factor. Remember, this is called a depressed polynomial because it's 1 degree lower than the original polynomial. That's going to go right here. So at this point, we know 6x to the third plus 19x squared plus 2x minus 3 is equal to x plus 3 times 6x squared plus x minus 1. Okay, so technically it's factored, but could we factor more? Let's look at this trinomial and see if we could find numbers that multiply to be negative 6 and add up to be 3. Or I'm sorry, add up to be 1. I was ahead of myself. 3 and negative 2 would do that, right? So if we factored this trinomial, we'd get 6x squared plus 3x minus 2x minus 1. Cutting it down the middle, we could take out a 3x. We could take out a negative 1. And we'd get 2x plus 1 times 3x minus 1. So as far as what the answer would be, completely factored, we'd have the x plus 3 that we were told times 2x plus 1 times 3x minus 1. Those are our factors. And if we wanted to convert those to roots, we can make them equal to 0. And x would equal negative 3. Bring the 1 over, divide by 2. Negative 1/2. Bring the 1 over, divide by 3. And these would be considered x-intercepts, zeros, or roots. So that's the difference between factors and roots. So now we're ready to move on to the main event. It's called the rational root theorem. Now what the rational root theorem is it's a 4-step process to find all of the rational roots of a polynomial. So if you go back to our chart we had up here, you always want to try using basic techniques and use more advanced techniques as required. So you wouldn't jump to use the rational root theorem unless it didn't factor or using quadratic formula didn't work. Remember, completing the square and quadratic formula only work for x to the second terms. So if you have an x to the third term, you're not going to be able to use the quadratic formula on that. So let's talk about what the rational root theorem is, and we'll go over a few examples. There's 4 steps. The first step for the rational root theorem is we find the number of possible positive roots. And the way that we find the number of possible positive roots is we determine the number of sign changes of f of x, and then subtract by 2 until you get 0. So what that means is if you figure out that there's 3 sign changes, meaning the problem goes from positive to negative, if it keeps going back and forth and that happens 3 times, you would subtract 2, and the 3 changes would be 3 or 1. It'll make sense when I show you an example. The second step is we find the number of possible negative roots. And the way we do that is it's kind of like what we did above, but first step we have to do is we change the signs of the odd powers of x. Meaning if you see an x to the third and it's like positive 2x to the third, x to the third is odd, so you make it negative 2x to the third. And then what you do is once you make those changes, then you determine the number of sign changes of f of x, subtracting by 2 until you get 0. For part 3, what we're going to do is actually list the possible roots. So we're going to list the possible rational roots. That's why it's called the rational root theorem, is it helps you find the rational roots. And those take the form of p over q, where p represents plus or minus factors of the constant or last term, and q represents plus or minus factors of the leading coefficient. Or first term. And then the last step is we're going to actually find the rational roots. And the easiest way to find the rational roots is we're going to use the remainder theorem to find a root, and then from there we're going to use synthetic division and factoring to find the remaining roots. So let's take a look at an example. We'll go through all 4 steps. Let's say f of x is equal to x to the third minus x squared minus 8x plus 12. Our first step is we list the possible number of positive roots. So look at your sign changes. X to the third minus x squared minus 8x plus 12. What are the sign changes? X to the third is positive, negative x squared is negative, negative x, and then positive 12. So how many times does the sign change from left to right? Well, it changes from positive to negative right there. Negative to negative isn't a change. Negative to positive is 1 change. So it looks like there's 2 total changes. And remember, we subtract 2 until we get to 0. So the number of positive roots is 2 or 0. Now let's figure out the number of negative roots. Well, we have x to the third minus x squared minus 8x plus 12. Okay, well, we're going to change the signs of the odd powers of x. So x to the third is odd. I'm going to make that, instead of positive, I'm going to treat it like a negative. X to the first is odd. So instead of that being negative 8, I'm going to treat it like a positive 8. And the even powers stay the same. Looks like there's 1 change. So you can't subtract 2 from 1. If you have 1 apple, you can't say you have negative 1 apples, right, if you subtract 2. So you subtract 2 until you get 0. So it looks like there's 1 negative root. Just as a side note, how many imaginary roots would there be? Well, there could be 2 or 0 positive. There's only 1 negative. There's supposed to be 3 total. So if there's 2 positive and 1 negative, there wouldn't be any imaginary. But if there's only 1 negative, there has to be 2 imaginary, so that when you add them together, you get 3. In order to figure out the imaginary roots, you don't go counting anything, you just make a table like this. For our third step, we're going to list the possible roots by writing P over Q, and P is going to represent factors of 12. So I know 1 goes into 12, 2 goes into 12, 3 goes into 12, 4 goes into 12, 6 goes into 12, and 12 goes into 12, over factors of 1. 1 is our leading coefficient. Well, if we write all of the top over all of the bottom, it's just going to be plus or minus 1, 2, 3, 4, 6, and 12. Those are our possible rational roots. Now for our fourth step, we have to figure out which ones actually work. So the way we're going to find them is we're going to use the remainder theorem, and we're going to plug those in for x. So I'm going to actually use my calculator for that. The way I use my calculator is I'm going to store those numbers so my calculator automatically plugs them in. First, I'm going to start with 1. So on my calculator, I'm going to hit the 1, I'm going to hit the store button, I'm going to go to A, and I'm going to hit enter. My calculator says, all right, 1 is going into A. The store button is in the bottom left-hand side. Now what I'm going to do in my calculator is I'm going to type in mem variable to get to A. So I'm going to hit mem variable A to the third minus mem variable A to the second minus 8 mem variable A plus 12 and hit enter. So when A is 1, or really when x is 1, I know that the remainder would be 4. And that's not what I want. 1's definitely not a factor, or 1's not a root because the remainder is not 0. I'm going to do the same process with 2. I'm going to store 2 for A, use the up button to go back to the equation that I typed in, and I get for 2, the remainder is 0. which means that 2 is definitely a root. So now what I'm going to do, according to the steps I outlined above, we're going to do synthetic division with 2 into 1x to the third minus 1x squared minus 8x and then 12. Bring the 1 down. 2 times 1 is 2. 2 times 1 is 2. And we do get a remainder of 0 using synthetic division. Our depressed polynomial would be x squared plus x minus 6. And now we're going to get the other roots by factoring this. That's what we outlined in our steps above. We used the remainder theorem to find a root. Once we got a root, we did synthetic division, and now we're going to factor to find the remaining roots. This factors down to be x plus 3 times x minus 2. And if we set those equal to 0, we get x is negative 3 and x is 2. So those are our roots, 2, negative 3, and 2. If we were going to graph this, there's actually a double root at 2. We'll talk about this in an upcoming section. But whenever you have a root that happens like multiple times, like we have 2 here twice, that's called multiplicity. What multiplicity means is that it happens a certain number of times. And if you have an even multiplicity, like 2 has a multiplicity of 2 because it happens twice, the graph's just going to kind of bounce off there. And that's what the graph would look like. The actual y-intercept here would be 12 when you look at the original equation and make all the x's 0. Let's try another problem. What if we had this one? F of x is equal to 2x to the third plus x squared minus 2x minus 1. Okay, we'll go through our steps. Step 1 is we find how many positive roots are there. Okay, so this is a positive, positive, negative, negative. Looks like there's only one positive root. And let's just look at the last example real quick. I just wanted to point this out. We said that there was going to be one negative, right? Here it is right here. We said that there was going to be 2 or 0 positive. Well, 1, 2. Technically they're the same number, but there are 2 positive roots. They just so happen to be the same number. This, by the way, these first 2 steps, that's called Descartes' rule. It's not really taught in a lot of pre-calculus classes, but I think it's important. It's a way to check your answers. If you're supposed to get 2 positive roots or 1 negative root, you can't be getting 2 negative roots. It just doesn't make sense. It's a way to check our answers. Okay, so we know that there's definitely going to be 1 positive root. For negative roots, we're going to change the odd powers. So this is odd, this is odd. So I'm going to treat it like negative 2, positive 2x. And it looks like we have 2 changes. So we're going to say 2 or 0. When we're looking for possible roots, p over q's, factors of 1 are plus or minus 1. Factors of 2 are plus or minus 1 and plus or minus 2. So we have to write all these combinations. We're going to write 1 over 1 and 1 over 2. Now let's figure out which ones actually work. Okay, so in my calculator, we're going to be plugging them into 2x to the third plus x squared minus 2x minus 1. Let's start with 1. If x is 1, I'm going to store that in my calculator. 1 store for a. And I'm going to type in 2 mem variable a to the third plus mem variable a to the second minus 2 mem variable a minus 1. And I get a remainder of 0. It's nice when it works on the first time. That means 1 is definitely a root. So now we're going to do synthetic division. we get a remainder of nothing, as we were expecting. Our press polynomial is 2x squared plus 3x plus 1. And we could factor this to finish. And it looks like they both would be positive. So if we set these equal to 0, we'd get x is negative 1/2 and x is equal to negative 1. So we got 3 answers. We're supposed to get 2 or 0 negative. Here's the 2 negative. We're supposed to get 1 positive. Here's the positive. As far as what this graph would look like, there's a root at negative 1, negative 1/2, and 1. If you look at the original problem, the y-intercept would be negative 1. So let's connect the dots. That's what the graph would look like. It's cubic, and cubics look like a squiggle like that. We're in a decisive parabola. We'll do one more. Let me show you. This is like the hardest kind of problem you would see with this. What if we had f of x was equal to 4x to the 4th minus 65x squared plus 16. So there's supposed to be 4 total roots. The number of positive roots. Well, we have a positive, negative, positive. The only time we plug zeros in is when we're doing division, but that's not what we're doing here. Looks like that's a change and that's a change, so there are 2 or 0 positive roots. For the number of negative roots, well, there's no odd power, so there's nothing to change. So it looks like, again, we have 2 or 0 negative roots. For our p over q, factors of 16 would be 1, 2, 4, 8, and 16. Factors of 4 would be 1, 2, and 4. So let's write all of the top over all of the bottom. Now there might be some duplicates and we don't have to write it twice. So let's try it. I'm going to write 1 over 1, 1 over 2, and 1 over 4. I'm going to write 2 over 1. Now 2 over 2 I already have. That's the same thing as 1, right? So I don't have to write that. And then 2 over 4 I already have. So I'm not going to write the duplicates. So I wrote 2 over everything. Now I'm going to write 4 over everything. 4 over 1, 4 over 2, and 4 over 4. 8 over 1, 8 over 2, 8 over 4. So you can see there are some duplicates. And then 16 over 1, 16 over 2, and 16 over 4. So those are all of our possible rational roots. Let's see which ones work. First, I'm going to start when x is 1. Generally, I try all the positives, and if I don't land on something, I'll try all the negatives, but usually there's always a positive. So I'm going to store 1 for a, and in my calculator, I'm going to hit 4 mem variable a to the 4th minus 65 mem variable a squared plus 16. And my calculator is telling me this is giving us a remainder of negative 45. So now I'm going to move on to 1/2. And if I store 0.5, do the problem again, I get a remainder of 0. So that's definitely one of the 4 roots. I'm going to use synthetic division and divide 1/2. But I am missing terms here. So remember, whenever we divide, we have to use zeros if there's no number there. So we have 4x to the 4th, no x to the 3rd, negative 65x squared, no x, and then 16. So this would be 4, 2, 2, 1, negative 64 times 1/2 is negative 32. So negative 32 times 1/2 is negative 16, remainder 0. And our depressed polynomial would be 4x to the 3rd plus 2x squared minus 64x minus 32. Now this factors. If it didn't factor, we could use rational root theorem all over again and get this down to a quadratic. And from a quadratic, we could factor, complete the square, or use quadratic formula. But this one actually factors also. We could take out a 2x squared. We're left with 2x to the first plus 1. Take out a negative 32. We're left with 2x plus 1. And we'll get 2x plus 1 times 2x squared minus 32. Setting these equal to 0, you'll get x is negative 1/2. So at this point we have one positive and one negative root. And then we get 2x squared minus 32 equals 0. Bring the 32 over. Divide by 2. And take the square root. You'll get x is 4. And remember, this is absolute value because you took the square root of something squared. So x would be 4 and x would be negative 4. We have two positive roots, two negative roots. As far as what the graph would look like, here's 4, here's negative 4, here's 1/2, here's negative 1/2. The graph's going to have a y-intercept of 16. So just like a very, very rough sketch is going to look something like this. Okay, let's move on to something else. What if I asked you to write a polynomial with degree 3 whose zeros or x-intercepts or roots are, we'll do two examples, -1, 2, and 4, and f of 1 is equal to 3. Okay, so this is how this is going to work. Let's write an equation f of x, and it's going to have a constant times, well, one of the roots is -1. If we bring that over, a factor would be x plus 1. One of the roots is 2. If we bring that over, one of the factors is x minus 2. One of the roots is 4. If we bring that over, another factor would be x minus 4. So the way this is going to work is let's multiply those out, and then we'll be able to utilize that f of 1 is equal to 3. So I'm just going to go ahead and FOIL these. This would be x squared minus 2x plus x minus 2. Or x squared minus x minus 2 times x minus 4. So now I'm going to have to distribute those two. So I'm going to multiply x squared times each term, negative x times each term, and then negative 2 times each term. Alright, and looks like that's what we get. Okay, so now let's use this whole f of 1 is equal to 3. Okay, so f of 1 would be 3, and we're going to plug in 1 for all of these x's. And we get a times 1 minus 5 plus 2 plus 8. That's f of 1, and that's equal to 3. So negative 4 plus 2 is negative 2, plus 8 is 6. So it looks like a would just be 1/2. So as far as what our actual equation would be, f of x would equal 1/2 times x to the third minus 5x squared plus 2x plus 8. And if you wanted to finish this, you would get 1/2 x to the third minus 5/2 x squared plus x plus 4. That's what our equation would be. It's a lot of work, but it's not really hard work. Bottom line is you make your roots into factors, you multiply out your factors, and then you figure out what a is by plugging in for x. Let's do one more like this. What if I asked you to write a third degree polynomial, so we're building off of this example, where one of the roots is -2 with a multiplicity of 3, and f of -1 is equal to 4. Well, that means that f of x would equal a times, well, multiplicity of 3 means that -2 is a root 3 times. So let's turn those into factors. And then we could distribute those. So it'd be x to the third plus 2x squared plus 4x squared plus 8x plus 4x plus 8. So f of x would equal a times x to the third plus 6x squared plus 12x plus 8. Now, if we know f of -1, is equal to 4, now we could figure out what a is. -7 minus 2 is, or -7 minus 12 is -19. So let's see what that is. I'll just use my calculator real quick. -19 plus 8 would be -11. So we get a is equal to -4/11. And our answer for f of x would be that we would have -4/11 times x to the third plus 6x squared plus 12x plus 8. And if we wanted to distribute that in, f of x would equal -4/11 x to the third minus 24 x squared over 11 minus 48 x over 11 minus 32 over 11, something like that. So it's not the prettiest thing, but that's how you would do it. Okay, move on to a different example. Let's talk about just quickly the conjugate theorem. Conjugate theorem says that it's actually called the complex conjugate theorem. Complex conjugate theorem says that if a plus bi is a root, so is a minus bi, the conjugate. We talked about conjugates. We were talking about simplifying complex expressions. So an example would be to write a polynomial function of least degree that just means don't make up any more roots, having zeros 3 and 2 plus I. So those are two roots, but you're expected to know that if 2 plus I is a root, so is 2 minus I. And the way we're going to get our polynomial is just like in the last problem. We're going to turn these roots into factors. by bringing them on the other side of the equal sign. And I'm going to go ahead and distribute out the complex numbers first. So I'll do x times x, x times negative 2, x times I, negative 2 times x, negative 2 times 2, negative 2 times I, negative I times x, negative I times negative 2, and then negative I times I is negative I squared. So let's simplify this. So I see negative 2i and positive 2i cancel. Plus ix minus ix cancel. I get negative 4x. And I'm going to have plus 4 minus I squared, which we know is negative 1. So 4 plus 1 is 5. Now to finish this, we'll get our polynomial by just distributing here. So x times x squared is x to the third minus 4x squared plus 5x minus 3x squared plus 12x minus 15. And that's what I did. So our final answer for this would be x to the third. Looks like we have minus 7x squared plus 17x minus 15. All right, so let's finish up here. Let's try this. Find all zeros, not factors, of p of x given a 0. So we're just looking at different combinations to find all the zeros of a polynomial. So we'll do 2 here. What if I told you p of x was equal to x to the third plus 4x squared minus 5, and one of the roots was 1. Well, that means one of the factors, we could figure that out. If one of the roots is 1, that means the factor would be x minus 1. We just don't know what else it's being multiplied by, right? So we would just do synthetic division to figure that out. If I told you 8 is equal to 2 times what number, you would divide both sides by 2. So I'm going to divide x to the third plus 4x squared minus 5 by 1. And let's see what we get. So we have an x to the third, we have an x squared, we have an x, and we have a negative 5. We just get x squared plus 5x plus 5. That's what it's actually multiplied by. That's our depressed polynomial. And that's not going to factor. So I asked you for all the zeros, right? So one of the zeros is 1. We usually factor to get the zeros, but we can't do that here. So let's just use quadratic formula real quick. Negative b, or the opposite of b, plus or minus square root of b squared minus 4ac, all divided by 2a. And I'll just use my calculator here. 5 squared minus 20 is 5. So we do get 3 answers. 1, negative 5, plus or minus root 5 over 2. How about one more like this? What if I told you that p of x was equal to x to the fourth minus 7x to the third plus 18x squared minus 22x plus 12. and one of the roots was 1 minus I. Well, we automatically know another one. So one of the roots is 1 minus I, which means another root is 1 plus I. We're supposed to have 4 total. So let's convert this to a factor by bringing everything here on the other side. We'll distribute those. This turns into x squared minus ix. We just distributed x times everything. Now let's distribute negative 1 times everything. Then we'll distribute I times everything. And summing this, we get x squared, the ix plus ix, negative I cancel. And we get 1 minus negative 1. So 1 plus 1 is 2. And we're still missing 2 roots. So what we are going to have to do, can't do synthetic division, we'll just long division, divide x squared minus 2x plus 2 into x to the 4th minus 7x to the 3rd plus 18x squared minus 22x plus 12. So x squared times what is x to the 4th? You always look at the first numbers. It's going to be x squared, and I'm going to multiply x squared times each of these. Remember to subtract. And we get negative 5x to the 3rd plus 16x squared minus 22x. Now look at the front numbers. X squared times negative 5x gives us negative 5x to the 3rd plus 10x squared minus 10x. Subtract these. And we get 6x squared minus 12x. I'll bring down the 12. X squared times 6 is going to give us 6x squared minus 12x plus 12. And if we remember to subtract these, we get a remainder of 0. So as far as what our factors are, factors would be, I have them right here. These are the 2 factors that we know to be x minus 2 times x minus 3. So if we're going to list all of the factors, we have x minus 2 and x minus 3, which give us the roots. If we make those equal to 0, we get x is 2 and x is 3. And then we also had the other roots to start with, right? We knew that x was equal to 1 minus I and x was equal to 1 plus I. And in factor form, this would be x minus 1 plus I and x minus 1 minus I. I believe the question asked us for our roots. So those are the roots. And our last type of example for this section, we're just going to be practicing some more of Descartes' rule. We're going to determine the different possibilities for the numbers of positive, negative, and complex roots. So really this is just the first 2 stages of the rational root theorem. I just wanted to go over these a little bit more in depth. I have 2 examples. So let's say we have one problem where f of x is equal to x to the 3rd plus 2x squared plus x minus 10. Well, the number of positive roots, we're looking at the signs of this polynomial. So we have a positive, a positive, a positive, and a negative. There's only one positive root because there's only one change. For the number of negative roots, we're going to change the signs of the odd powers of x. So we're going to have negative x to the third, positive 2x squared, negative x, negative 10. Changes once here and once here. We're reading from left to right. So there's 2 or 0 possible negative roots. Table that we've been doing, we're going to have number of positive, number of negative, number of complex, and our total. So it looks like number of positive roots is 1, but there could be 2 or 0 negative roots with that. There's going to be 3 total. So it looks like there's no imaginary roots or complex roots if we have 1 positive and 2 negative, because that adds up to the total. But if we do have 1 positive, there would have to be 2 imaginary to come up with our total of 3. Last problem. What if we had f of x is equal to 3x to the fourth plus 2x to the third minus 8x squared minus 10x minus 1? Well, first step, let's figure out the number of positive roots. We have a positive, positive, negative, negative, negative. There's one change. The number of negative roots, we're going to change the signs of the odd powers of x. So we're going to have a positive, negative, negative, positive, negative. Looks like we have a change here. 1, 2, 3. Or 1. Remember, we always subtract 2, and so we can't do it anymore. You can't subtract 2 from 1, you'd get a negative number. So as far as our possibilities, there's 1 positive root, but there could be 3 negative with that, or there could be 1 negative with that. Total, there's 4. So if there's 1 positive and 3 negative, there's no imaginary. If there's 1 positive and 1 negative, we still need 2 more left over. All right, so that's how we use Descartes' rule.